For question 3, we're told to use the integral test to determine the convergence or divergence of the sum from 1 to infinity of the natural log of I divided by I squared. And, helpfully, we're reminded to verify the conditions of the integral test. And one of the reasons the integral test is not typically an appealing test to use is because it does have a pretty substantial set of requirements. If we look at the function that corresponds to the terms of the series, so in this case, that would be the function natural log of x divided by x squared, we have to make sure that that function is continuous, is positive, and is decreasing on the interval from 1 to infinity. Well, we're told that we have to use the integral test for this question, so let's make sure that it works. So we'll let f of x, as I say, be the function ln x over x squared. Now, is this positive? Well, certainly. As long as x is bigger than 1, we know that the natural log function is a positive number, and of course x squared is always positive. So this is definitely positive, and it's also definitely continuous, because we're only going to run into a problem either at x equals 0, because that would make the denominator 0, and of course we can't divide by 0, or at any negative value of x, because we can't take the natural log of a negative number, or 0, which we've already discounted. And none of those values of x are on the interval that we're interested in, where x is strictly greater than, where x is greater than or equal to 1. So we can just immediately say that this is positive and continuous for x greater than or equal to 1. Always the most challenging of the 3 requirements to confirm is that it's decreasing. Sometimes that's pretty obvious, but in a case like this, I think we can be pretty confident that that's the case, but we'll want to make sure. And our tool for making sure of that fact is the derivative. So we can also say that by the quotient rule, f prime of x in this case is the derivative of the numerator, 1 over x, times the denominator x squared, minus the derivative of the denominator, 2x, times the natural log of x from the numerator, divided by x squared all squared, which is x to the 4th. We can simplify that a bit. We get x squared divided by x is x, but that means now that we've got a common factor of x everywhere in this expression, so we'll divide that through, and that'll give us 1 minus 2 times the natural log of x divided by x cubed. Now, is that a negative quantity? Well, when x is 1, no it isn't. When x is 1, the natural log of 1 of course is 0, so we just get 1 over 1 cubed, which is 1. But as soon as we get much bigger than that, certainly once x is at least e, Euler's constant, where the natural log is equal to 1, we're going to get at least negative 1 over whatever x is cubed, and it only gets more and more negative from there. The bigger x gets, the more negative the numerator is, and the denominator is always a positive number. So this is definitely less than 0, and we can say for x sufficiently large. So this tells us that our function is decreasing, or at least is decreasing eventually, which is really all that the integral test requires. So are the conditions of the integral test met? Yes, they are. Now the question is, can we apply the integral test? So now we have to evaluate an integral, which is the other reason the integral test is not always our favorite test, because the improper integrals we get can sometimes be pretty intimidating. In this case, we're going to have the integral from 1 to infinity of the natural log of x over x squared. And because that's an improper integral, the first thing we're going to need to do is rewrite that as a limit. So I'll replace the upper bound, the infinity, with a dummy variable, capital T, and I'll take the limit then as capital T goes to infinity. So now we're integrating from 1 to t the function natural log of x over x squared. This is an integration by parts problem. It's not a u substitution problem because there's not really a good candidate for u in this case. If it was the natural log of x over x, it would be ideal, because then we could let u be the natural log of x, and 1 over x dx would be equal to du. But because we've got that power of 2 in the denominator, there's not really any expression here whose derivative is also present in the integral. So we'll try parts instead. So we're going to use integration by parts. And let's see, the thing that we differentiate, I call that w. I know most textbooks call it u, but, well, we've got u substitution, which uses the letter u very conveniently. And sometimes we want to do a u substitution with an integration by parts. So I use w because, damn it, there are 26 letters in the alphabet. The thing we're going to differentiate is going to be the natural log of x, because we don't have to integrate that. If you remember from Math 1001, the natural log of x, in order to integrate it, we need to use integration by parts again. And ideally, when you're setting up integration by parts, the thing that you differentiate should get simpler when you differentiate it, and the thing that you integrate should be an elementary integral. So we'll let w be the natural log of x, so that dw is 1 over x dx. And that means that we have to let dv be whatever's left over, which is 1 over x squared in this case. And so v is the antiderivative of 1 over x squared, which is negative 1 over x. So the integral becomes, well, we've still got this limit hanging around. So the limit as t goes to infinity of v times w. So that's negative 1 over x times the natural log of x. And that's going to go from 1 to capital T. And we'll worry about evaluating that once we've done all the integration. Minus the integral of v dw. So minus, I'll take the minus that's associated with v out of that integral to make this a plus the integral from 1 to t of 1 over x times 1 over x, which is 1 over x squared. Well, now that's an elementary integral left to us, which is ideally what we want to see for integration by parts. So I'm going to have the limit of the natural log, negative the natural log of x over x, that we already had there, plus the integral of 1 over x squared, which is minus 1 over x. And that's going to go from 1 to t. So that'll be the limit of, let's see, when I plug in t, I get negative the natural log of capital T over t, minus 1 over capital T. And then when I plug in 1, well, the natural log of 1 is 0, so the first term goes away. Then plus 1 over 1, which just gives me 1. And 2/3 of these terms are very easy to handle. The limit of 1, of course, is just 1. It's constant. The limit of 1 over capital T as t goes to infinity is 0. The only tricky one here is the natural log of t over t. That's an infinity over infinity indeterminate form, so we need to use L'Hopital's rule. So under L'Hopital's rule, we're going to get, well, let me write the 1 that we already had out front, so that there's no implication that's still part of our limit. So 1 plus the limit as t goes to infinity of negative, well, we need to divide the natural log of t with respect to t to get 1 over t, divided by the derivative of the denominator. Derivative of t with respect to t is just 1. And now that's a pretty simple limit. So now that's going to be 1 minus the limit as t goes to infinity of 1 over t, which is 0. So the entire improper integral evaluates to give us 1 minus 0, which is 1. And bear in mind, that quantity, the fact that it's equal to 1 specifically, doesn't really have any significance. All that matters is that this is a convergent improper integral. And what the integral test tells us is that if the improper integral is convergent, then so too is the given series. And if the improper integral is divergent, well, the given series is divergent as well. So we can conclude that by the integral test, the sum from 1 to infinity of the natural log of I over I squared must be convergent. And there's the integral test out of our here, and we'll kind of keep our fingers crossed that maybe that was the only time we actually had to use it on this exam.